Hi, in this class I will be teaching you electromeric effect and hyperconjugation. So, we will be starting the class with electromeric effect. This is the only effect in your course which is temporary. It is not a permanent effect in the molecule. Now, in this effect, pi electrons, they tend to shift towards one of the atoms. So, if you have carbon-carbon double bond, one bond will be sigma, the other one will be pi. Now, if this pi bond shifts completely towards one of the carbons due to an attacking reagent, then it is called as electromeric effect. Now, let's take one example. Let's say we have this carbon-carbon double bond and we add H plus to this. Due to presence of H plus, this carbon-carbon pi bond breaks heterolytically. Heterolytic means both the electrons will be taken by single species. So, if this carbon takes away both the electrons, this will become negative, the other one will become positive. H plus will attack or join with the negative one. So, you will end up with something which looks like this: C, C, H plus. Now, there is a complete shift of pi electrons to the carbon on which the attacking reagent is adding. This is the carbon which is taking away the pi electrons, and to this the attacking reagent is adding. This is a temporary effect because if I remove this H plus from the medium, again carbon will form a double bond. So, this is not the permanent effect, it only happens in presence of a reagent. If the attacking reagent gets attached to that carbon which is getting the electrons, then we call it as plus E effect. Or the easier way to memorize this, if you have positive charge, look at this, you have a positive charge, then you call it as a plus E effect. Let me tell you the other one. Let's say this is carbon-carbon double bond and Cn negative is attacking on this. Again, due to presence of Cn negative, these pi electrons are taken by this carbon. So, this will be negative, this will be positive. Cn is going to attack on which one? The one which is positive. So, you will end up with C, C, Cn, and this will be negative. This is minus E effect. What is the net charge on this? Negative minus E. If the net charge is positive, this is called as plus E. The technical definition: if the attacking reagent attaches to the carbon which is getting the electrons, then it is plus E. If the attacking reagent attaches to the carbon which is not getting the pi electrons, then it is minus E. This is the technical definition, but if it is negative, then it is minus E. If it is positive, it is plus E. And the most important thing that you need to know about this effect is that this is temporary. If you remove the reagent, the effect will go away. Now, let's see how this is given. It is a temporary effect. This is the first line. The organic compound having a multiple bond, a double or triple bond, show this effect in presence of an attacking reagent only. This is the definition. It is defined as a complete transfer of a shared pair of pi electrons to one of the atoms joined by a multiple bond on demand of an attacking reagent. The effect is annulled, that is cancelled out, as soon as the attacking reagent is removed from the domain of the reaction. That means if you remove H plus or Cn negative, carbon will again form double bond between themselves. It is represented by E and the shifting of electron is shown by a curved arrow. Positive electromeric effect plus E, in this pi electrons of multiple bonds are transferred to that atom to which the attacking reagent gets attached. So, look at this. So, this is getting the electrons and H plus is joining with this, then you call it as plus E, or simply this is positive. So, this is plus E. Negative electromeric effect. In this effect, the pi electrons of the multiple bond are transferred to that atom to which the attacking reagent does not get attached. For example, this Cn, so this is negative, Cn is getting attached to this one which is not getting the electron. When inductive and electromeric effects operate in opposite direction, the electromeric effect predominates, and the reason is, in inductive effect there is not complete transfer, in electromeric effect there is complete transfer of electrons. I hope this is clear. Now, let us come to the next topic. Now, the next topic that we are going to do is hyperconjugation. I will take the example of propene to explain you hyperconjugation. Propene is CH3 CH double bond CH2. There is double bond between these two carbons and there is single bond between these two carbons. So, if we name them 1, 2, 3, there is a double bond between 1 and 2 and there is a single bond between 2 and 3. This single bond between second and third carbon is of shorter bond length than an ordinary single bond. If you take ordinary ethane, it has carbon-carbon single bond. This single bond between second and third carbon is slightly shorter than that. Now, carbon and hydrogen as atoms do not possess lone pair of electrons. Hydrogen has 1 electron and it will always form 1 bond. Carbon has 4 electrons, it tends to form 4 bonds across organic chemistry. So, they never possess lone pair of electrons. We can explain why this carbon-carbon bond is shorter using the concept of hyperconjugation. Now, let us see what happens in this. So, you have propene, and between first and second carbon you have a pi bond. In pi bond there is sideways overlapping like this. Now, this sigma bond between CH, this one, this overlaps with a pi cloud. So, this is what is happening. These sigma electrons come over here. Now, this carbon will not be able to form 5 bonds. So, this pi bond breaks and comes over here. So, your next structure will look like this: H, C, H, H plus, double bond, C, H, single bond, CH2, negative. Now, just try and understand what is happening in this. In resonance, lone pair moves. In hyperconjugation, bond pair is moving. This is a bond pair. This is moving like this. Now, this carbon will not get affected because instead of having bond with hydrogen, now it is going to have bond with carbon, but this hydrogen loses this electron. So, it has become H plus. Now, instead of this hydrogen, it could be this hydrogen also. Then our structure would have looked like this: C H plus H H double bond C H CH2 lone pair negative. It could have been this hydrogen also, then our structure would have looked like this: C H H H plus double bond C H CH2 negative. Now, there are 4 structures which we can draw for propene. The actual molecule we assume is in between these structures, and if you look at structure 2, 3, 4, there is double bond between these 2 carbons, and this is able to explain why this bond is shorter. So, hyperconjugation is exactly same as resonance. Do not know the exact position of electrons. We say such molecules have many structures. Likewise, in hyperconjugation also the molecules have many structures. The actual molecule is in between all these, but instead of lone pair, in hyperconjugation what is moving is the bond pair of electrons. Now, when you draw these structures, in structure 2, 3, 4, there is no bond. Actually, if you look at this, there is no bond between carbon and hydrogen. No bond here, no bond here. So, hyperconjugation is also called as no bond resonance. So, in your exam, if you get a question, what do you mean by no bond resonance? Your answer is, this is hyperconjugation. Now, hyperconjugation, apart from explaining why the single bond in propene is shorter, can also explain the relative stability of carbocations. Now, this relative stability of carbocations we had done through inductive effect, and now we are going to do the same thing using the concept of hyperconjugation. Now, let us take, we are explaining the stability of carbocation. So, let us say we have CH3 CH2 plus, this is a primary carbocation, and if you want to be specific, this is ethyl cation. Now, how hyperconjugation is stabilizing this? This is what we are going to look at. C H3 C H H plus. We have just expanded the structure. Now, this carbon has 3 bonds, but carbon has 4 valence orbitals. This electron pair is given to this carbon in the empty orbital. So, the next structure will look like this: H C H H plus double bond C H H. Because this carbon has effectively gained 1 electron, the positive is gone. Now, this could be this H, again this H. So, next structure could be like this: H plus C double bond C H H H H, or the third one. So, the last structure could be like this: C H H H plus, double bond C H H. If you look at these structures, they are very similar to propene. Now, what is happening? There is dispersion or delocalization of charge. Look at positive charge, it is dispersing. Positive is on one carbon, then hydrogen, then this hydrogen, then this hydrogen. Dispersion or delocalization of charge always makes the species more stable. Now, in this case of primary carbocation, there are 3 hydrogens which can be involved in hyperconjugation. Now, come to think of it, had I given you this, in this case this is a secondary carbocation, there are 6 hydrogens which could have done the same. So, the charge would have spread on 6 hydrogens, more dispersion. And had you got a tertiary carbocation, the positive charge would have spread on 9 hydrogens, 3, 3, 3. Greater the dispersion of charge, more the stability. So, according to hyperconjugation also, the stability of carbocation is tertiary is more stable than secondary is more stable than primary. So, hyperconjugation can explain us the stability of carbocation. We have already done this topic of stability of carbocation using inductive effect. Now, you can write the answer using either inductive effect or hyperconjugation, both are correct answers. Both can explain why tertiary carbocation is more stable than secondary and secondary is more stable than primary. Now, when you draw hyperconjugative structures, you always transfer sigma electrons, and the structures which are formed, they sometimes do not have any bonds between atoms. That is why it is called no bond resonance. One other thing which hyperconjugation can explain is the stability of alkenes. Now, we will take these 2 examples. This is but1-ene, this is but2-ene. Now, if you are asked which is more stable, very similar molecules, same molecular formula, they are isomers also. The neighboring carbon to the double bond is called as alpha. So, this is alpha, this is beta. In this case, the double bond carbons are in the middle. So, this is also alpha and this is also alpha. The neighboring carbon to the functional group is alpha. So, this has 2 alpha hydrogens, the second one, this is only 1. The hydrogen which is attached to an alpha carbon leads to hyperconjugative structures. So, there are how many hydrogens, alpha hydrogens in this case? There are only 2 alpha hydrogens, whereas in this case there are 6 alpha hydrogens. If you have more number of alpha hydrogens, there will be more dispersion of charge, that will be more stable. So, if you are asked but1-ene, but2-ene which is more stable, your answer is but2-ene, because it has 6 alpha hydrogens. So, it will have greater number of hyperconjugative structures. Now, if you look at propene, propene is this, it has 3 alpha hydrogens. Look carefully, this is the double bond, these 2 are involved, this is the neighboring carbon, how many hydrogens? 3. So, this has 3 alpha hydrogens. So, we have drawn 4 structures for propene. If there are 6 alpha hydrogens, then there will be 7 structures. So, more the structures, more the dispersal of charge, more the dispersal of charge, more the stability. So, if I give you one more alkene which looks like this, CH3, C, CH3, double bond CH, CH3. This is 2-methyl but-2-ene. Now, where do you place this one in stability? This will be less stable or more stable than but-2-ene? Just think about it. Your answer has to be more stable. These are the double bonded carbons. So, this is also alpha, this is also alpha, and this is also alpha. Alpha is a very simple position to understand. The neighbor is called alpha. So, this carbon is forming a double bond. Which are the neighboring carbons? 3. So, there are 9 alpha hydrogens, which means among these 3, 1, 2, 3, third is most stable. So, greater the number of hyperconjugative structures, more the stability. Hence, among these 3, 2-methyl but-2-ene tends to be most stable. Now, this is how hyperconjugation is given. Hyperconjugation is a general stabilizing interaction. It involves delocalization of sigma electrons of CH bond of an alkyl group directly attached to an atom of unsaturated system. So, CH bond which is directly attached to an unsaturated means double or triple bond, or to an atom with unshared p orbital, like in case of carbocation, it had an empty p orbital. The sigma electrons of CH bond of the alkyl group enter into partial conjugation. This simply means they are sharing electrons with the attached unsaturated system or with the unshared p orbital. Hyperconjugation is a permanent effect. Now, to understand hyperconjugation, let us take example of ethyl cation, in which the positively charged carbon atom has empty p orbital. One of the CH bonds of methyl group can align in the plane of the empty p orbital. So, you have something like this. This methyl is aligning with the empty orbital of this carbon. This is what is written over here. Now, what will happen? And the electrons constituting the CH bond in the plane of p orbital can be delocalized into empty p orbital as depicted. So, this is CH3 and this is sharing electrons with the empty p orbital of CH2 plus. This is CH2 carbon plus. So, this is how we showed this. This comes over here and there is a double bond. So, the next structure you can draw like this, H C C H plus double bond CH2. So, this positive has dispersed from carbon to hydrogen. Now, this is how they have shown in over here. This type of overlap stabilizes the carbocation because electron density from adjacent sigma bond helps in dispersing the positive charge. Look at these 4 structures very carefully. So, if I draw the arrows, it will be like this in this. This will be your structure. Now, had I made the arrow like this, the structure would be this, or the third is this hydrogen comes over here. So, how many structures in this case? 4. In general, greater the number of alkyl groups attached to a positively charged atom, the greater is the hyperconjugation interaction and stabilization of the cation. Thus, we have the following relative stability of carbocations. So, this is tertiary, secondary, ethyl, methyl. This has no alpha hydrogen, positive. This has 3, this has 6 and this has 9. So, tertiary carbocation in this case will be more stable. Hyperconjugation is also possible in alkenes and alkyl arenes. Delocalization of electrons by hyperconjugation in the case of alkenes can be depicted like this. Now, what they have shown, this is the example of propene. This is carbon-carbon double bond. This is carbon with hydrogen. So, this double bond like this is how they have shown. This is the double bond, and this sigma electrons are being shared with this. So, this we had previously shown like this arrow. So, now they are showing it with a wave just to depict how this is happening. So, this is how we had done this. So, double bond, the adjacent CH electrons come into interaction with those pi clouds. And lastly, they have given the hyperconjugative structures of propene. There are various ways of looking at hyperconjugative effect. One of the ways is to regard CH bond as possessing partial ionic character due to resonance. So, this is propene, this H, so H plus so will be over here. If it is this H, then this one structure, and if it is this H, this is the structure. So, total number of structures is 4, which we drew over here. We had 4 structures, 1, 2, 3, 4. And you must remember, in an alkene, if there are greater number of hyperconjugative structures, alkenes will be more stable, and those hyperconjugative structures depend on number of alpha hydrogens. The hyperconjugation may also be regarded as no bond resonance. So, remember, it is similar to resonance. Instead of lone pair, in hyperconjugation bond pair moves. So, if you are moving bond pair of electrons, like I am moving a bond pair of electrons over here, then you do not call it as resonance, you call it as hyperconjugation. I hope this is clear. In case you have any doubts, you can always ask me. Thank you.